right, so what we're looking at here is we're going to be looking at the limit of this particular function, which is x y squared, all divided by x squared plus y squared. We're going to be looking to find this limit as this for this function as x and y approach 0, 0. So one of the first things that I'm doing here is I am going through and I am defining how we're working with this limit. And one of the first things that I want to do is I want to observe that the actual function is going to be greater than 0, but only when we take the absolute value of that function. So we want to kind of hold on to that, and then we want to say, hey, let's go ahead and let's make all these changes into polar coordinates. So if I let x is equal to r cosine theta and let y is equal to r sine theta, then the function naturally becomes r cosine of theta times r sine of theta, quantity squared, all divided by r squared. With some algebra manipulation, this will then turn into r is multiplied by the absolute value of cosine of theta times sine squared theta, and that's for the absolute value. Now, if we can naturally start thinking about this, then any values for cosine theta are going to be outputs. In other words, they're going to be ratios, which means that this portion here will be a fraction that's less than 1. Think about this guy here too, sine squared. If sine is a trigonometric ratio between 0 and 1, or let's say negative 1 and 1, then naturally when we square it, it's going to be an even smaller fraction. So we're multiplying a small valued fraction times a small valued fraction. Naturally, it's going to be smaller than 1 itself, which means as we proceed forward, or as we continue to move forward, that means that that whole quantity will then be less than or equal to r. Equal when, of course, cosine theta times sine squared theta is equal to 1. That means that as we're looking at the limit comparison as we described or as we generated in the previous line, we're now looking at the limit for that function as x and y approach 0, 0 is going to be less than or equal to the limit as r is approaching 0. And again, this is because as we start looking at the conversion between x squared and y squared, being that r is defined as the square root of x squared plus y squared, if x and y are going to 0, then naturally r must be going to 0 as well. So then this will then naturally imply that as we're looking at this limit, we're going to get that the limit will in fact be equal to 0. And as you can see, I'm finishing my thoughts here. Now, looking at that problem, here's that surface that we're looking at. All right, so here's the surface that we're looking at for that function, which was that x y squared all divided by x squared plus y squared. Now, I'm going to embed that polar curve on this particular surface. Notice that the theta value will then just capture, if we're looking down at the x and y coordinate system, it's going to capture this whole path. But notice that path is kind of restricted by the surface. So as we start moving through this surface, theta just moves around in a circular fashion along the surface. But if r is then subject to change, then r is just going to either make that curve larger or it's going to make it smaller. Now remember, we defined that r value going to 0. Now we defined it specifically because our ordered pairs were approaching 0, 0. So you can see as r values get smaller, this curve starts converging on one specific point until we get the actual output of z is equal to 0. So that then naturally shows you that you can still parameterize curves using polar coordinates, and they should still get you the exact same evaluation as if you didn't use polar coordinates.